Good morning, friends. So we are back with fluorescence spectroscopy again. Now, in our last lecture, we talked about this spin chemistry and magnetic field effect on exciplex luminescence. So, you know, the time scale of observation of such events like this spin chemistry processes. Okay. So, these are typically of the order of nanosecond. Now, the point is why I am emphasizing on the time scale, because of the fact that in case of spin chemistry, that is dealing with spin system that spins basically, you know, precess about some magnetic field direction. So, what is happening that this precessional frequency is dependent on the external magnetic field or the magnetic field experienced by the spin itself. So, when the magnetic field increases, this precessional frequency becomes more and more, and when we talk about this singlet to, you know, this singlet to triplet interconversion, okay. So, this spin rephasing process. So, spin rephasing process means it is basically dependent on the difference in the precessional frequency, and since this precession is typically of the order of nanoseconds, so you can observe these processes, this spin chemistry, I mean the dynamics of the process in the time scale of nanosecond, okay, typically time scale of nanosecond. Now, so that is one side of, you know, one side of this application of fluorescence spectroscopy, where we use the fluorescence techniques, okay, where we use the fluorescence techniques by, I mean, to find out these processes, I mean to find out the effect of, I mean to quantify the effect of external magnetic field on this exciplex luminescence. Today I am going to talk about another topic which is very important in chemistry, okay, and that is solvation and how, I mean, how this process is taking place as a function of time, that is the dynamics of solvation. But before going into the details of it, I just want to remind you about one point, that regarding the detection of this, I mean a small point I should you know, I should mention over here regarding the detection system that is required to you know, to monitor this magnetic field effect on exciplex luminescence. One thing is that that we are measuring the amount of fluorescence or the fluorescence intensity, you know, in fluorescence intensity in absence of an external magnetic field and in presence of an external magnetic field. And the point is, you know, if the effect is very small, I mean this effect of external magnetic field on fluorescence intensity is very small, in that case you can find out, still you can find out by means of a technique which is called phase lock loop system, in which this magnetic field is modulated. Modulated means this magnetic field strength is modulated, giving a, I mean with a sine wave, you know, sine wave function, that is your magnetic field is going up and down, okay, with time. I mean, it follows a sine function, and in your detection device is also modulated in such a way that it can detect only this phase modulated signal. So if there is any noise or something else there, then this phase sensitive detection system will just eliminate those things, because noise is basically random. But if there is any real magnetic field effect, then only phase modulated component, if we just monitor the phase modulated component, then out of many other things we should be able to extract only the magnetic field dependent part. So this way we can detect this magnetic field modulated this exciplex luminescence by means of a phase sensitive detection by using a lock-in device. Okay, that actually finishes this. I mean, this small indication just gives you an idea how to find out, or how to know how much is the magnetic field dependent thing. Anyway, so now let us switch on to this solvation. Now solvation is a very important process. Okay, solvation means that you have, suppose you have sodium chloride. Okay, you sprinkle some sodium chloride in water. What is going to happen? That this, if you look into the crystal of sodium chloride, then you will be finding that with time this crystal is becoming smaller and smaller, and ultimately the whole crystal is getting solubilized. I mean, getting solvated. That is, a solution is formed, and it is homogeneous in nature. The solution is homogeneous. So what is happening, that you have got this sodium ion and chloride ion which are located in the crystal lattice of sodium chloride, and this water molecule is going to penetrate in between the sodium ion and chloride ion, so that this electrostatic force of attraction between this plus ion and this minus ion is getting reduced because of this Coulombic factor, because Coulomb force is Q1 Q2 by epsilon r square. So epsilon is the dielectric constant, or the polarity of the system. That's a measure of the polarity of the system. So if it is more polar, then your force is reduced a lot, and as a result of which they will just go out of this crystal lattice, and and sodium ion and chloride ion, these ions go into the solution. Okay, so you get a solution in which the sodium ion is solvated, and also chloride ion is solvated by these water molecules. Okay. Now the question is is it possible to know this? Is it possible to get information about this solvation, whether this solvation is very fast, or this solvation is very slow, or this solvation does not at all take place? Okay, so definitely solvation is taking place, because sodium chloride goes into the solution. So in order to explain this solvation behavior of different solute, various models have been proposed. Okay, so basically to have an idea of the effect of solvent on various chemical processes, because solvent is a very important constituent for chemical reaction to take place. If you don't have a solvent, then you cannot do some reaction which occurs within the solvent. Maybe gas phase reactions are possible without solvents. Now many reactions take place in solution. That's quite obvious. Like reactions in our body, that also takes place within some solvent. Then also another important thing is that not only these biological reactions, but reactions what we do in the industry, maybe in the laboratory, or maybe in the research laboratory, you need to have solvents. Maybe in some solvents some reactions are becoming very fast, in some solvents maybe reaction does not at all take place. Okay. So, proper choice of solvent is very important in chemical processes. Now, so short range I mean what is the role of solvent? Role of solvent is that typically concentrated in the first solvation sphere, that is the sphere which is close to the solute. Examples could be like hydrogen bonds, preferential orientation near an ion like this. So you see that you have got this solute, this is your solute, and this is your means if you can draw a sphere near this green circle, then these are the solvent molecules, maybe water HOH, this is HOH. So water molecules are lying out there. Okay. So they will what they are going to do, they will tend to form hydrogen bond with this. If this is an electronegative negative, it has electronegative atom, or maybe since it is a dipolar system, I mean this water has got dipole moment, so it will tend to stabilize. If it is an ion, then it will tend to stabilize by means of dipole ion interaction, thereby reducing the energy of the system. Okay. And maybe this can be a typical, this dotted thing can be a typical hydrogen bonding manifestation. So this is hydrogen bonding. So in that case, maybe hydrogen bonding making a chain of hydrogen bonds. Okay. Or this is hydrogen bonded wire, you can think of as if it is behaving like a wire. Hydrogen bonded wire means it is a long wire, you can think of. Okay. Now what these means these are short range things. Now long range effects are like polarization. So charge screening, basically polarization means so from long distance, this like you have got a dipole over here, so this dipole is going to induce another dipole in the nearby area, and as a result of which maybe some induced dipole is created, and so that this material is getting polarized. Okay. So that's called the polarization of charge maybe. Now models like in order to explain this different behavior of different solvents, some solvation models have been proposed to explain the behavior. Now the point is, why do I need to talk about this different models and this introductory thing while I talk about this this fluorescence spectroscopy? Because fluorescence spectroscopy is a very useful tool, and very sensitive technique, okay, to know various, to monitor various processes, of which solvation is another very important process. And in some cases solvation is very fast, in some cases process of solvation is very slow, and you can monitor using a specific designing your experiment in a suitable way. You can monitor the process of solvation. You can also monitor the time course of the process, time course of solvation. Now regarding the solvation model, some describe explicitly the solvent molecules, some of them treat solvents as continuum. Basically it is a continuum of dielectric, that is, it is a continuous material, as if you have got your molecule over here and it is dipped into a continuum of molecules. The description over here and description over there remaining the same. And in some cases there is a combination that is called the hybrid of these two models. And in that case it treats first solvation sphere as explicitly, while the surrounding solvent, remaining part of the solvent by a continuum model. Okay. Now continuum model means it is also known as the reaction field model, and in that case consider a solvent as a uniform polarizable dielectric medium with dielectric constant epsilon, and in which you are placing the molecule M. Okay, so this is your dielectric epsilon, and the cavity, you can design the cavity suitably, like suitably in the sense that it may be a spherical cavity, it may be something else also. Generally, spherical cavity is easy to deal with, because I mean this model is easy to deal with. Okay, and it is a more simplified model. Okay, so so that's the continuum model, and now Unsager model is basically similar to that. Is a spherical or ellipsoidal cavity, and radius from the gas phase structure of the molecule, and empirical radius from density and molar mass. Choice of radius is important for the accuracy. Charge distribution of solute expressed in terms of dipole and multipole expansion, and especially multiple expansion is needed for non-polar solid. Multiple means, dipole means 2 poles plus minus, multiple means more than 2. Okay. And electrostatic interactions, in this case it is calculated analytically. Electrostatic interaction means electrostatic force of interaction, that is your Coulomb force. Whatever calculation is required, it is analytically calculated, and it is a simplified and although it is an approximate, but this simplified model has been found to be very good in many cases. Okay, this is your Unsager model, Unsager reaction field. Now, when we talk about the solvation, then one thing always comes into mind, that is your solvatochromosome. Solvatochromosome means it's a phenomenon that change of color due to change of solvent. Change of solvent means change of solvent in terms of change in terms of the polarity of the solvent. Okay, so that is solvent polarity dependent color of the substance. Okay, so this is nothing but the change in spectral position of the absorption or luminescence band. Okay, so why this is happening, I will come to that, but the point is this solvatochromosome is very much important in reference to your this solvation. Okay, in reference to solvation, because when there is solvation, then you need to have, suppose you have got a gas phase molecule or gas phase atom. Okay, it is not at all solvated by solvent molecules, so it will have some energy, and the moment it is poured into a solvent, then it will be surrounded by solvent molecules, and if it goes into the solution, that means it is accepted by the solvent molecules. And why accepted? In the sense that the solvent molecules are welcoming this guest. Okay, and welcoming means there is a favorable interaction between this this solute and solvent, so that it prefers to stay over there means in solution rather than in the gas phase. So if it prefers means its energy is lower, that means it is thermodynamically stable. Okay, so thermodynamically stable, and that's why it goes into the solution, and it has been found that when you change the solvent, then there is a change in spectra. Maybe in some cases spectra is shifted a lot. Say in one solvent it is red, and in another solvent it becomes violet. Okay, so this particular thing, I mean this particular observation, you can explain in terms of the existing model of solvation. Okay, so basically whatever I am talking over here right now is on the equilibrium solvation. Okay, so till now I have not talked about anything on the process which is a time dependent one. So first we would like to understand what is the solvation in terms of equilibrium model, and then maybe we can extend it further to this time dependent phenomena, that is extend it further for the transients. Okay. Now you see that this is a dipolar molecule, and of course absorption and luminescence band, and due to the change in polarity of the medium. So change in spectral position, that is absorption and luminescence band due to change in polarity of the medium. That is very important, that is called solvent chromosome. Now this is a dipolar molecule, this is a dipolar substance which is it can luminous, and this is dipole interaction. You have this dipole, you have another dipole, so there is an interaction. So it as a result of this interaction, the energy level of the molecule in question is getting modified. Okay, and that is the reason for the solvent chromosome. That is, your actual energy level is getting affected as a result of this dipole interaction or interaction with the solvent. Maybe if it is a polar solvent, then polar solvent will interact with the dipole, leading to this stabilization of the dipole that is in question, and therefore energy level is further lowered. If the energy level is further lowered, accordingly you can see that by means of a spectrophotometer or maybe by means of a fluorimeter if it at all fluoresces. So spectrophotometer means you just monitor the absorbance spectra of that molecule. So solvation is a physical perturbation perturbation to this fluorophore or lumophore molecular state. So in that case we must consider one thing, that in this case there is no solvent induced processes like proton transfer, electron transfer, ionization, complexation or isomerization and so on. So solvent induced such processes are not there. So that is very important, that is that particular assumption should be applicable over there. Okay. So we are just talking about the solvetochromosome. Okay. Now let us look into this diagram. What is happening? That you have got your dipole, okay, and this is your solvent molecules with properly oriented solvent molecules. This blue part means it is blue and white means this side is it is having some charge and this side is having some charge. So charge nature is opposite, charge separation is there. So you see that this dipole, is surrounded by the solvent molecules, and of course this is a polar solvent molecules. Okay. So in this case, because of the change in the energy state, as a result of interaction between the solvent and your dipole in question. Okay. So you see there are two situations. Okay. In one case, this is your ground state dipole, the ground state, this is your excited state, and suppose that your excited state dipole moment is more. Okay, mu1 means your excited state dipole, it is more polar in the excited state. Now the question is, why it is more polar in the excited state? Why there should be a change in dipole moment when you photoexcite a molecule? Is it true for all the cases where there is photoexcitation? In most of the cases, if it is a dipole driven excitation, electric dipole induced transition, then in most of the cases you will be finding that there is a change in dipole moment in the ground and in the excited state. So what is that? Suppose you have got a molecule, say something of this sort. I am not drawing exactly the structure of the molecule. So in the ground state, suppose the electron is distributed, electronic structure is such that, electron distribution is such that electron is distributed all over the molecule. Okay. So molecular orbital is like this. Now you excite this with appropriate frequency. So what is happening? So in this molecule what will happen, that maybe because of this photoexcitation, majority of charge is now displaced to this region, and maybe few electrons are there. Okay. So, therefore, this part is delta plus and this part is delta minus. So, a dipole is induced. Okay. So, because of this electron redistribution in the excited state with respect to the ground state, there is a change in dipole moment in the excited state compared to the ground state. Now, if you increase the polarity, what is happening? Polarity, if you increase the polarity means, this is the expression, I mean the amount of stabilization that you are going to expect when there is a change in dipole moment. So, basically delta E is the change in stabilization, whether it is stabilized or destabilized. It is your delta E is equal to delta mu dot E. Mu dot E means mu dot maybe something, I mean that is related to the electric field that is experiencing this dipole moment. Okay. And that has got some connection to the polarity of the system. Okay. So, if this is more, then this mu is more, then you can expect more stabilization compared to this one, because this mu is less. So, ultimately if you increase the polarity, you will be finding that this gap is reduced. So, initially this absorbance spectra, I mean if you record the absorbance spectra, you will be finding that this gap is more. So, it is absorbing in the bluer side, and now it is absorbing in the red side. So, therefore, there is a shift, and that shift is called bathochromic shift or red shift. Now, you compare the other situation, that ground state is more polar, okay, than in the excited state. So, therefore, ground state will be more stabilized. More stabilized means you can expect the reverse trend, that hypsochromic shift or blue shift, that your absorbance gap, and consequently the emission frequency is also, if it emits from S1 to S0, then emission frequency for low polarity solvent and for high polarity solvent, you will be finding that for low polarity solvent its emission will be in the red side, and here it is in the blue side. Okay. So, therefore, this solvent polarity, I mean invoking the idea of solvent polarity, you can explain this solvetochromosome. Solvetochromosome means solvent polarity dependent color of the system both in emission and in absorbance. Okay. So, there is a typical example that if you increase the polarity, then you will be finding that the polarity that it is shifting towards the this side. Okay. So, this is a red shifted behavior absorbance spectra in various solvent of coumarin 153. That's a dye, and it's taken from this example. So, therefore, solvetochromosome can be negative, solvetochromosome can be positive, as I have explained it over here, that in this case you have this red shifting, and in other case you have the blue shifting. Okay. In dipole-dipole interaction model between chromophore and solvent, when dipole moment is reduced after excitation, a negative solvetochromosome, that is the blue shift is a blue shift is expected, as it is explained over here. You see that dipole moment is less, okay, but if the dipole moment is more, you can get the reverse trend. So, studying the solvetochromosome in terms of fluorescence and absorbance, you can actually guess, or you can guess means you can get the idea of the fact that whether the substance is having greater dipole moment in the excited state than in the ground state, or the reverse. Okay. Okay. So, solvetochromosome in absorption and emission spectra. So it is typically an equation, quantified by an equation by Lippert and Mataga, and with appropriate reference. So, a spherical cavity dipole solute. Solvent interacts with the electronic transition by virtue of the change of solute dipole moment from G to E, solute's dipole moment, as a result of transition from ground to excited state, that is mu G to mu E. And transition frequency is expected to vary with solvent dielectric property, and which is, you know, as per this Lippert-Mataga relation. Okay, this is the frequency. Okay, this 1 to 2, and this is the mu 0, and then this A is some parameter. Okay, so this is solute dependent parameter. A is due to the polarizability of the solvent nuclear coordinate, and B is due to the electronic polarizability of the solvent, where A and B, these two are expressed like this. So now this reaction field factor obtained from dielectric continuum theories of solvatochromic shift is this, where N is the refractive, this is your dielectric constant, N is the refractive index of, that is refractive index of the medium, and by using this, if you plot, you know, this as a function of, say, you know, epsilon, you know, as a function of dielectric constant of the medium, okay, or if you plot this, you know, nu 1 2, maybe you know, this is your static dielectric constant and refractive index of the solvent. These are now you can, in principle, I mean, if you know this one, and from this, I mean, this is for your so what is happening exactly, that knowing this, I mean, how much of shift is there, okay, how much of shift is there when with respect to a low polar solvent to your unknown solvent. From this you should be able, after knowing this, you should be able to find out, you know, this factor where this is your solute radius, or if your solute radius is known, you should be able to calculate the maybe this excited state dipole moment. Okay, so this way, you know, this way you should be able, I mean, you should be able to quantify the solvatochromism in, I mean, by measuring the solvatochromism in absorption and emission spectra, you should be able to find out maybe this unknown quantities, maybe this A, or maybe this mu E, or maybe mu G, depending on which one is unknown. So these are very important things. So solvatochromism is a very important factor, you know, and the idea of this solvatochromism is very important in understanding the solvation behavior. Okay, solvation behavior when some solute is dissolved in some solvent. Okay. Okay. Now solute-solvent interaction, two categories. One is short range microscopic interaction, another is long range interaction, that is electrostatic interaction in dielectric continuum. In case of this this continuum model. And reaction field, the electric field which acts upon the dipole as a result of electric displacements induced by it on I mean, because of its presence. Okay, by its on presence. So because means why I am talking about the electric displacement, because it is basically an electric displacement. So you see that electrons are now displaced from here to here. So why you know, this is happening? Because whenever you shine with radiation, then radiation is an electromagnetic radiation. So this electromagnetic, as a result of this electromagnetic interaction between the electromagnetic radiation and your matter, you know, this molecule is excited from the ground state to another level, and because of this excitation, you know, this dipole is created. Maybe a change in dipole moment is there. Okay. And in this case, you know, a dipole is placed within a cavity of radius a, as I told you over here, that it is placed within a cavity of radius a, and it is a continuum dielectric. It is in a dielectric continuum. Okay. So so regarding the solvetochromosome, in case of hemicyanin dye, you can expect this negative solvetochromosome. Okay, so positive solvetochromosome you can also expect for there are plenty of examples you can find. Okay, so therefore solvetochromosome is a very important thing, I mean important phenomena which we will try to utilize in understanding the solvation behavior of molecules. Okay. Now solvation is important for understanding the solvent effects on chemical and biochemical system. Okay. And in biological systems various processes such as transportation, signaling, metabolism are controlled by solvation. Okay, so solvent plays a very important role. Solvent plays a very important role. Why solvent plays a very important role? Because in some of the cases electron transfer, suppose you talk about electron transfer, that is redox couples that are there within cells. So what is happening that this electron is maybe it is transferred through the solvent, through water molecule, or maybe through something else. So sometimes solvent is important in transferring the electron. So since there is solvent, so solvation can be a very important factor. Changes in local polarity by solute-solvent interaction in such systems can be related to impaired function of something. Okay, so impaired function means whatever system you are talking about, so that system may have impaired function because of this change in local polarity of a molecule in question. Okay, so variety of solvent polarity parameters have been proposed. I mean this polarity, because polarity is the key factor for showing this solvetochromosome. Okay, so you see, as I told you that excited mu is greater than ground state mu. So in gas phase, so whenever you put basically more polar, then what is happening, that excited state and ground state is progressively stabilized because of this, and reverse situation can happen in case of the opposite situation. So commonly used dyes that can be used, okay, can be used to understand the solvent effects or solvation effect in chemical and biochemical systems. Okay. Now solvent relaxation. What is solvent relaxation? You see that what you basically do is whenever you talk about this fluorescence spectroscopy and solvation and dynamics of solvation, then the point that we always should remember is that you are taking some fluorophore, okay, and you excite the fluorophore to some electronically excited state. So there is a change in dipole moment, and that fluorophore in the excited state is going to emit some radiation, okay, and you are monitoring that radiation. But the point is, in this case it is not just a steady state process. Okay, it is not just a steady state process. Point is, whenever we talked about this solvetochromosome, okay, that is say blue color to red color as a result of change, as a result of change of solvent polarity. So that talks about, that is basically an equilibrium description of the system. That is, you start from one equilibrium state in one solvent, and then when you change the solvent, then it is placed into another equilibrium situation in another solvent. Okay. So you do not have any time information, time resolved or time dependent information of what is exactly happening to the energy state, okay, whether the energy state is changing with time or not, or something else is happening, whether that can be monitored spectroscopically. Okay, spectroscopically means time dependent behavior, whether that can be monitored spectroscopically, that we are going to focus under the heading of solvent relaxation, and of course using fluorescence spectroscopy. Now the point is, when you start with this type of description, I mean this type of technique, that is use of fluorescence spectroscopy, then you should remember that we have to have a good spectrometer capable of recording this time resolved information. That means you need to have short pulse of radiation. Short pulse of radiation may be typically several nanosecond, some nanosecond, maybe 1 to 2 nanosecond, or maybe some picosecond, or maybe some femtoseconds. Okay, so your pulse width, I mean you need to time gate the process. I mean you need to get the time gated information. Okay, that is, you start your reaction, say this is your short pulse of radiation. Okay, so like this, so this is your pulse, short pulse. So the moment it enters into your sample, the reaction has started, and then there is no pulse. What you do, the moment it starts, I mean in moment it enters into your sample, the time counting has started, and then you with respect to that time counting, that is your time zero, you monitor this information, that is maybe fluorescence, as a function of time. Okay, and that will give you the idea of how much time it is taking. That is the point is, you are creating an excited ensemble of molecules M star. This is your M by your radiation h nu, excited ensemble of molecule, and then so it is a dipole with different mu excited. So this is your mu g. So what is happening, the moment it is created, so it will face some solvent molecules. Okay, some solvent molecules in a given configuration. Okay, so what will happen, that these solvent molecules are facing, okay, this newly created dipole. So newly created dipole, initially that newly created dipole was not there. So it's a problem to them that suddenly when they see that there is a dipole, so they will tend to stabilize it, because it is the natural consequence that it is an energetically, it means you are creating an energetically unfavorable situation. So energetically unfavorable situation means the system will try to reduce its energy. But the point is, these dipoles, they will require some time. Okay, they will require some time. Why they will require some time? Because electronic transition that takes place very fast, because electrons are very light particle. But suppose you have a dipole like this is your minus side, this is your plus side, and suppose this is also this transient dipole that is created as a result of excitation, and suppose this is your solvent molecule. Okay, so the moment it is created over here, you see that this minus and that minus, okay, they are trying to repel each other. Okay, so in order to get a favorable orientation, that is energetically lower situation, lower configuration, so it will start to reorient itself in such a way that the energy is minimized. So think about the fact that in this case, not only this solvent molecule, but there are other solvent molecules in the surrounding of this transient dipole that is created as a result of photoexcitation. Okay, so therefore it is a complicated event that all the solvent dipoles will tend to orient themselves in such a way that this gets stabilized. Some of them are already oriented in a proper direction that they don't need to reorient to reduce the energy of the whole system. So they are not going to, maybe they are not going to take part, but the other solvent molecules are going to reorient themselves to reduce the energy of the system. Okay, but remember one thing, that this rotation takes time. It is not all on a sudden, so it takes time. So therefore, what is happening, that progressively this dipole, I mean this excited state, basically this excited state is getting stabilized. Okay, because with time this configuration, this description, this solvent molecules, okay, that is the solvent configuration, that is suppose there are 100 solvent molecules surrounding this dipole. So, that surrounding solvent molecules, they are going to reorient to reduce the energy of this system, energy of this molecule. So, progressively this is stabilized, okay, energy wise it is stabilized, okay, like this. So, you see that it is basically, it is basically shown over here that maybe this molecule has got a dipole in the ground state. So, that dipole value say something mu g, okay. So, with respect to this dipole, these solute molecules or solvent molecules are oriented in such a way that it gets the lowest possible energy, okay, in that solvent, okay. So, that is your ground state and denoted by equilibrium ground state. Why it is equilibrium? Because it is equilibrium in the sense that it is the lowest energy situation, okay, lowest energy situation. So, equilibrium ground state, okay. So, like what you see in case of what I talked about in case of solvator chromosome, okay. So, you see that this is your ground state. Now, you shine with radiation over here, okay. So, therefore, this is mu g and this is your energy, ground state energy, okay. So, therefore then it gets excited to the other to the higher level. So, it is a non-equilibrium situation. Why it is a non-equilibrium situation? Because you see that solvents are remaining over there as if the solvent molecule, okay, the solvent molecules, these are static. So, it is basically a Franck-Condon excitation. So, Franck-Condon means this electronic transition is taking place in the static nuclear coordinate, that is nuclear coordinate is not changing, okay. So, and the transition is denoted by a vertical line, that is no change in nuclear coordinate, okay. So, therefore, this solvent molecules are still remaining like this, and you have got this dipole, that is a changed dipole over here, okay. So, changed dipole over here. So, therefore, so it is a non-equilibrium situation, energetically higher. So, it will tend to the system will tend to minimize its energy. So, what will happen then after this, within the lifetime of this dipole? So, suppose this is your dipole that is created. So, and suppose you have got other solvent molecules, say these are the solvent molecules like this. So, it will eventually, what it will do, it will just try to orient, so like this, to get a minimum energy configuration maybe. So, what is happening, maybe say this is your minus side and this is your plus side. So, maybe this way they will tend to orient themselves. So, initially it was like this. So, they will orient this way, maybe this is one configuration, another like this configuration, another like this configuration, this way. So, this is one way of realizing how the system is getting stabilized. So, what is happening, that this is your non-equilibrium excited state, then it will tend to go to an equilibrium excited state. So, equilibrium excited state means it must have energy which is, it must have this electronic energy which is lower than this non-equilibrium excited state, okay. So, it is you see that solvent configuration is different. So, you started from here excitation, then this is your Franck-Condon excited state, and then progressively it is going to here, okay. So, and of course, for that it requires some time. So, progressively it goes to some equilibrium excited state, and say this corresponds to a composite coordinate that denotes this electronic state of this molecule and this solvent atmosphere. So, what is happening, that excitation, then Franck-Condon to equilibrium excited state, then fluorescence, or maybe it can fluoresce from here as well, okay, here from I mean here from here to here, here to here. So, you will be seeing, and then ultimately this is the lowest configuration, lowest energy configuration, from which it will also emit, okay, giving rise to a red shifted, most red shifted emission. Here you can also get red shifted emission compared to this emission, compared to this you can get emission over here, that is emission from non-equilibrium excited state, or maybe it is similar to a locally excited state. So, you see that it is the most red shifted emission which you are getting from here, and then after reaching over here again this is an equilibrium, I mean non-equilibrium ground state. Non-equilibrium means the solvent configuration is such that although it is in the ground state, but it is somewhat less stabilized. So, what will happen? It will tend to move to this one by again by solvent reorientation, solvent reorganization, and therefore, maybe this excess energy will be given to the system by means of heat. So, here you can get emission, here you can also get emission. So, basically if you can get a system which has the capability of doing time resolved measurement, then you can with time you can see this evolution, with time you can see this evolution, that is you know, it is like your locally excited state. So, locally excited state will quickly depopulate, but this particular state initially at 0 time, immediately after excitation, this population is not there. So, you at 0 time maybe you will not get emission, I mean you will not get anything, but after some time this population will be built up. So, emission will increase and then it will decay. So, therefore, you will be seeing a rise time maybe at the red end of this spectrum. Okay. So, this is what we can do in your you know solvation dynamics experiment. Typically, we take some dye, we take some fluorophore, and we do this measurement, that is time resolved, this time dependent measurement, to to find out this time dependent information, that is time dependent fluorescence information. Okay. So, today, I mean in this particular lecture what we have learnt is I just give you a basic idea of solvation, and then solventochromosome, and a brief introduction about the solvent relaxation process, means how the solvent is relaxing after a transient dipole is created around it from an equilibrium ground state, I mean while going from an equilibrium ground state to a non-equilibrium excited state. Okay. So, that is all for today. I mean in the next lecture we will have more discussion on solvent relaxation with more pictorial descriptions. So, till then have a nice time. Thank you.